Oh my gosh. Okay, good afternoon. Okay, I have to say that Luna and Sam get a double, well, and Ashley. Okay, good afternoon, everybody. But wow, Luna, that avatar, that thing is awesome. And Sam, if in a totally different way, that thing is awesome. Um, wow. Okay, that's hilarious, Luna, and I totally agree with that. And I agree with the Beatles, of course. Who doesn't? And in the physics you make is equal to the physics you take. Okay, wait. No, yeah, that is great. That is great. And okay, wait. So yeah, no, that's totally, and is exactly the way I feel. Well, both is how I totally feel inertial. I feel like Newton's first law right now. But I also feel like I'm in a yellow submarine. Actually, I did, well, anyway, okay. John Lennon loved physics, by the way, but anyway, whatever. So yes, good afternoon, Luna. I mean, who doesn't love physics? Hello, besides everybody. Hello, Ashley. Good afternoon, Jenna. I mean, you're welcome. I mean, hello, Sam. Hello, Luna. Yes. Hello, Stephanie. And oh yeah, yeah. Oh, the get back thing. Yeah, although depressing, right? I mean, yeah, I mean, I'm sort of psyched for it, but I'm sort of like, that's such a depressing, but yeah, yeah. But it's not Yoko's fault. That's my only point. And good afternoon. And by the way, is that who, can I just ask, I mean, Ranclis Milan, can I ask, I don't recognize that. Is that someone else's device or who? But thank you for saying good afternoon, but who are you actually? That's a different name from the one you usually use. Ms. Milan or Mr. Milan? Can I just ask who?
What's my sister name? Because she was using my computer.
Oh wait, who? So sorry. So who? Wait. So who? So who? Oh, okay, great. Oh, good to see you. Thank you. Okay, that totally makes sense. And thank you for telling me. And it's good to hear your voice, which I don't usually get to hear. Great. Okay, all good. And it's funny too. I'll say. I mean, not that I worry about. I mean, like last night I did a Zoom with my family over something, and my brother, and like I said, give me the Zoom link, and he sent me the Zoom link with a password, and I'm like, password? Like who? I mean, really? Are we worried about security issues when we're like doing a holiday thing? But I guess I never think about like who the heck wants to, be an uninvited guest to a physics class. So I wasn't really worried, but it's good to know who you are. Okay. All right. So we have to thank you for indulging me on Tuesday. I know I was out sick, and I know the year is winding down and we're getting there. Let me just switch. We have, some stuff left to do. And some stuff and stuff to get back, so to speak. Pardon me for a second. Well, quick question though, for you to please put in the, and I am feeling a little bit under, I mean, to be honest, I mean, I'm not feeling totally up to speed here. I apologize in advance if this is rocky or whatever. But quick question, can someone please tell me, or can any of you or all of you tell me in the chat or otherwise, what is your next thing that's due, or what is due in lab, if I may ask? Because I want to, if I
we actually have formal lab 4 due tomorrow, but we pretty much are all done with it. And then we are supposed to be close to finished with lab 5, according to him yesterday from lab. Wow. But I know I'm not, but we're supposed to be midway with lab 5.
Oh, that's very helpful. And thank you for using your voice, by the way, Ashley. That's, I mean, I can always rely on you. That's great. Okay, no, that's really helpful. And let me make sure, and wow, formal lab is due tomorrow, but you're pretty much done. And lab 5 is the circuit, is the Ohm's law one, and lab 4, is that correct? Wait, no, well, I'm sorry, remind me, lab 4 is the make your own wave animation thing, and lab 5 is the Ohm's law one, like the circuit one. Is that correct? Or oh, sorry, the chat. Correct. Oh, totally correct. Amazing. Okay, you'd almost think that I understand this course. Okay, great. Well, what that does mean, and then okay, That's actually perfect, especially, yeah, we talked so much about waves and everything. If you're done with, but if you're in the middle of lab 5, then that's good, because that means what I want to do today, that helps me with what I want to do today, and it'll make, I think, what I want to do today even more relevant. Are you, okay, last question. You're in the middle of lab 5. Are you going to have something will you have to turn in something about lab 5, like a formal report? Because sometimes when the year starts running out like this, I don't know what, sometimes they make adjustments. So is there going to be a thing due for lab 5? Do we know, or did you already answer that and I'm not understanding? Sorry. As I said, not sure. Okay, well, that's fair. Okay, well, that's all right. But lab 5 is what you're in the middle of. So I think this will be helpful. Okay. In other words, you are talking about circuit. You are dealing with circuits are on your mind in lab. That is correct. Correct. I mean,
That's correct.
Yeah. Okay, great. Thank you. And thank you, Ashley. And thank you, Luna. And thank you, Sam. Great. Okay. And it's not too late to submit for points for any of that. Oh, and another quick thing, by the way, if any of the game assignments were due, if they said they were due December 1st, which I think some of them might, that's arbitrary. Don't worry about that. Like December 1st was just meant like toward the end of the semester, and I'll readjust. Like certainly nobody should worry about. I mean, you could still, any kind of game assignments that have to do with doing extra things or getting extra points for any, this is the time to survey back and look, like, did you ever help out a colleague in the middle of a discussion? Did you ever say something that was wrong? All those like bonus, whatever you want to call them, game term things. This is the time to turn them in, but don't worry about don't worry about them being late or something like that. Okay. All right. So let's talk circuits. Okay. What I want to try to do today is relate the notions of electrostatic charge and electrostatic field, which are electrostatic concepts. I want to try to relate them to what you're worrying about in lab, which are really more electrodynamic concepts. You're looking at circuits in the lab, electrical currents running through simulated wires and through resistors and from and back to batteries. And what we had been talking about in class, like last week before Thanksgiving, and then what I was talking about on the videos, which I really do hope you watch, and I'll say something about that again, but what I've been trying to get across in the lecture background is what the notion of an electrostatic field is, and I'm trying to relate that back to gravitational fields, which are in turn related back to gravitational forces. So, I mean, in short, conceptually, again, and I may want to review this again, like formulaically in a second, but in short, the electrostatic field is the force created by an electrostatic charge. It's the force waiting to happen. Right. In fact, okay, I'm going to review this for 2 minutes now before I go any further. But let me also say, please do watch that video that I posted Tuesday when I was sick. It is doubly long. I mean, it's a double lecture, but I've missed another class here or there for sure. The material is very relevant to now. I mean, I made the video a couple semesters ago, but it's very, very relevant to now. You might have noticed that, I give you points just for even confirming that you get my sick message, whatever. But then if you even show any slight indication in good faith that you made any attempt to watch the video, and at least one person already did this, just let me know, and then you get extra points for watching that video. The truth is, the video is class material. Like, you're sort of required to watch it anyway. I mean, it is class, but I know it's difficult to watch these videos on your own time, and it's a drag and all that. But also, please note that I didn't necessarily expect that you could necessarily watch it right away that day. Like, even if you could watch it during the weekend or something, it'll be very useful and help you put this material back together. And I mean, it's not a random video. It's us. It's me. It's this. It's just not us. You get it. But conceptual reminder of what. Yeah, maybe. All right. Yes. So let me remind you very briefly what an electrostatic field is. I mean, in principle, I've told you this a couple of ways, a couple of different times now, and in principle, it's in the video. But let me just remind you, what a field is. And let me say, before I even turn the page, and say, A field is something that exists anywhere and everywhere and all the time, and exists, or arguably many fields exist simply by virtue of objects existing. When certain types of objects exist, they create fields. They don't have to do anything to create the fields. They just have to sit around and be, and they will create the fields. And what the fields are pulls or pushes acting on empty space. So this is why I call them pulls or pushes waiting to happen. And again, I will turn the page in a moment, but remember, a force necessarily, by definition, going back to the original mechanical context, the Newtonian context of forces, a force is a thing, a force is an interaction, it's an activity, it's an action that I exert on you, that one actual discrete object exerts on another object. A force is an interaction between two objects, like fundamentally and always and necessarily. A force is an interaction between two objects. Okay, I just want to summarize again, and hello, everybody. I just want to summarize again where we were, before Thanksgiving, before I was sick on Tuesday, and where we are in the videos and stuff. And again, my goal is to keep pushing a point that I'm trying to make in the lectures and relate it to what it is that you're trying to wrap up the year by studying in lab. So, and remember, please, at all times in the back of your mind that like the theme of this course, or the nature of this course, is that we're here trying to study the principles and practices of physics the good old-fashioned laws and predictions of motion as they are applied to non-material entities, right? That's really, again, the difference between physics 204 versus physics 203, or this physics 2 course, physics versus a physics 1 course, is that it's all physics. It's all the same practices and principles, and it's all the same goal, which is to study motion through the universe. The difference between physics 203 and physics 204 is that we're here is just the agents of action that we're studying. In physics 203, we were studying material, discrete, identifiable particles as they move through time and space, as they experience trajectories through time and space. And in physics 204, we're looking at the same rules, the same concerns, the same practices and principles. But now the entities that are moving through space are no longer material, particular, discrete entities. We spent a long time, most of the course, in fact, building up the notion of a wave pulse and then studying how it propagates through space. The whole point of all of that, of harmonic oscillation, of then a collection of phase staggered oscillators, and then the wave equation, and then the Doppler effect. All that stuff was to ultimately see how there could be motion from here to there of something that was never here nor there, if you see what I'm saying, right? Like sound, again, in my mind, I always bring everything back to sound. Sound was kind of like the centerpiece of this course in a way, like everything in a way was building up to sound and then from sound. Because sound, to my mind, is the most concrete, picturable, familiar example of a non-concrete type of motion, right? Again, I'll say for the 90th time, just to drum it in, like when I send a sound from my mouth to your ears, please always remember, if nothing else, remember, there is no thing that goes from my mouth to your ears. There's no discrete, identifiable material, distinguishable, bounded, massive object, none at all, that makes a journey from my mouth to your ears when I make a sound. Yet something clearly goes from my mouth to your ears. Now, that's an example of an immaterial motion. Everything that's happening even after the sound point in this course, even if it's all of a sudden it seems like we're talking about all these different things, like we're talking about electrical fields in the lecture, we're talking about electrical circuits in the lab, like what's this all about? Is these are now even more advanced and slightly even more esoteric maybe, but more useful maybe, or like equally useful versions of immaterial motions, right? That's the thrust of the whole course always is immaterial motions. And the hub of everything we're closing the course down with, I mean, the hub of what's going on in the lectures right now and going on in the labs is really that we're talking about these things called electrostatic fields. A field is in so many ways a very immaterial thing. Let me remind you, again, at the risk of boring everybody, let me remind you again what like a field actually is in English, and then I'll go back to the math. A field comes from the idea of a force, but it's different. A force is an interaction. So I'm like on the page now here. Like a force is an interaction between two material discrete particles, two things, right? Like I push you, you push me, or I pull you, you pull me. And a force, before I even go on and read anymore, remember, a force necessarily, always involves two actual objects that are interacting with each other, that are pulling or pushing on each other. But macroscopically, in the context of mechanics, in the context of like physics 203, often we identify the presence of a force by identifying or noticing some kind of physical contact between two objects, like the normal force or the frictional force or the tension force are all examples where I push you or I pull you by touching. Right. And generally speaking, the way we know whether something's being pushed or pulled in mechanics is if we observe some kind of touching, some physical contact between the two objects. So whenever we see two objects touching, we definitely say there's a force. And then often if we're looking for a force, we look to see if two objects are touching or not. However, there's some forces in the world, it turns out, that seem to be able to occur or happen without the presence of material contact, without physical contact, without touching, right? I mean, and again, at the risk of repetition, the gravitational force is one such force where by virtue of which the sun seems to be able to pull on the earth without any physical touching, or the earth seems to be able to pull on like a brick or chocolate without any touching. Similarly, protons seem to be able to pull on electrons, and protons seem to be able to push on protons through empty space, or as we say, at a distance without any touching. Now, this is a force, but as we discussed like 2 weeks ago, forces like this, at first, they kind of seem to be like an exception of some kind, like they kind of throw off our game and our whole notion of forces. And they do for good reason, because we at first wonder, and we ask a lot of questions like, how can one thing affect another thing without touching it at all? Especially when we start really looking at the math. Okay, well, yeah, we'll turn the page in a second. Once we really start looking at the math and realizing that when we see or observe gravitation occurring, or when we see the effects of electrostatics, the closer we look, the more we realize it's not just a qualitative phenomenon, it's a quantitative phenomenon. And the details are fairly staggering when we really think about it. What we really realize is that through gravitation and through electricity, objects pull on and push on one another in a manner that depends on properties of those objects. Like again, the sun pulls harder on the earth if the earth is bigger or if the earth is closer to the sun. And protons pull harder on electrons if electrons are closer to protons. And the thing that we said a couple of weeks ago that we raised is, well, this is sort of amazing, because if it's really true, it seems to mean that vital information, statistics, descriptions, numerical descriptions of objects, of their size and their whereabouts, seem somehow to travel through empty space or get held in empty space at abeyance or something, somehow get transmitted, propagated, conveyed through empty space, like all the time and all the place. It seems like objects are continually sending out signals describing their own size and their own whereabouts to all other objects in the universe at all times, because all objects seem to accelerate around in response to the whereabouts and the size of all other objects at all times. So apparently there's this ongoing exchange of information among all objects throughout empty space, which is like a really, right, which is like really a staggering idea. Like, even if you don't try to explain it at all, if you just say that it's true, it's sort of, at least to me, it's kind of mind-numbing that that could be the case at all. It's mind-numbing enough that I would not believe it. I don't think it intuitively makes sense. I'm not saying logically, obviously, the universe has to be that way. It's just that the universe does seem to be that way. Like, the universe does have to be that way if it behaves the way it seems to be behaving. Like, you know, things orbit around each other in numerical patterns that generate data that we collect. So as scientists, and again, this goes back to 2 weeks ago, Newton is sort of the first to really, really confront science in such a hard way that it rocked his philosophical soul. And he had to almost make a choice between his two personalities, between what he wanted to believe and what the data forced him to believe. And really, this is what science is all about. We're forced to say, look, it doesn't make sense. It's not the way we wanted the universe to be necessarily. If we were designing the universe, I'm not sure we'd come up with this, but apparently things communicate with other things at all time through space. So what we say is, now again, that's just the way it is, apparently. It's not the way it's just the way it is, apparently. So then we design some words and some models to help us get a cognitive grip on this the way it is. We come up with it just like we always do in science, and some predictive tools or some models to help us predict where things are going to be when, which is always the point of physics. So we say that from here on in, with any of the forces that seem to be associated with action at a distance, with forces like gravitation and like electrostatics, we say, okay, there's got to be a middle step there, or I don't know if there's got to be, but for our minds to handle it, we insert a middle step, a middle agent. We say, okay. However, this information is getting sent from the sun to the earth, or however the information is getting sent from a proton to electron, like we don't totally know. We're not pretending to totally know, but somehow it seems to be happening, and somehow information seems to be held. I mean, it makes a journey from the proton to the electron. And so somehow it exists in the empty space between the proton and the electron. So we have this idea of a field. The field is like a force, but it's an idea that we believe in and use only in the context of fundamental forces, of forces that act at a distance, right? So there's no such thing as a tension field, and there's no such thing as a friction field, and there's no such thing as a normal force field, but there is a such thing as a gravitational field and an electrostatic field. And just to remind you again, like it says here, the whole idea of the field is it's the intermediary, it's the third agent. A field is to fundamental information as the medium is to a wave pulse. The field is like a medium that apparently exists in space and that conveys and transmits or allows for the transmission of information from one object to another. And what we say from now on is instead, so like the page is trying to say here, a force is an interaction between two material discrete particles. A field is an action created by one particle. If you're a big grammar person in English, like what this really is, it's like the difference between a transitive verb and an intransitive verb, if that makes a verb, like if you've ever, I know maybe we don't love, I don't know how you feel about grammar or English or things like that. And this applies to other languages as well. But, in English, whenever you have a predicate, you have a subject. Like whenever you have a verb, you have a noun. Whenever you have an action, you have the thing committing the action. But sometimes predicates not only have subjects, they also have objects, if you ever think about it, right? So like sometimes I can just say, I stand, and that's like a subject and a predicate. I stand, subject, predicate. But sometimes I can say things like, or I sit, subject, predicate. But other times I can say things like, I sit on a chair, right? Subject, predicate, object. Chair is object, right? Like noun, verb, noun. And the first case is the kind of verb that's happening there is called an intransitive verb. It's just a verb, it's just an action that's happening. And in the second case, when there's a subject and a verb and an object, when the verb is actually doing something to something, we call that a transitive verb for whatever it's worth. I'm saying here now, I mean, I don't know if that analogy helps anybody at all, but I'm saying here now that whenever we have interactions between two objects that seem to happen in empty space, what we actually believe is that the first object creates a field in empty space. And then if the second object finds its way to any location in empty space, it experiences a force from that field, right? So again, just to remind you, in other words, right, just to So, I mean, in short, field is force per charge. It's the, and I don't even know, maybe the ones and the twos are even confusing. Right, but it's ultimate. The field is the medium that that comes into existence the minute the first charge comes into existence. The first charge comes into existence and it plops down information everywhere in space, at every single point in space. In fact, what it really plops down everywhere in space is a vector. Like literally speaking, what really happens is, and if the vectors, I'm putting the vector symbols in now because they actually make it clearer to me. If the vector symbols make it more confusing than to you, then leave them out. But I'm saying what really happens is, if you put a proton down somewhere in space, immediately, everywhere in space, there's a little vector that well, here, actually, let me draw this here. And tell me if you need me to go back to this page. But this page is just saying like proton creates field, then second proton sits somewhere in the field and experiences the force from that field. You want to know how much the force is that the second proton experiences? Multiply its charge by the field itself, and you get the force. What is the field? The field is all the information from the first charge. It's all the information of the first charge, like how big it is and where it is, times a constant. And so it's the, oh. Oh, wait, this is a really good question. So Sam's question, how are the equations for G and E force obtained? Really, really good question. The original equations, like the F equals GMM over R squared and the KQQ, those original equations, that is a great question. And that gets deep. For Newton, so gravity came like about 150 years before electricity. The gravity equation is a very big deal and very controversial. But basically, it's put together, it's inferred or induced from astronomical data. Like, it's not a definition, it is empirically induced. It was a big, he took a lot of data, like Kepler's data, Tycho Brahe's data, and put it together. And he wasn't the only one ever to think of this, but he did take astronomical data and make some major extrapolations and major leaps from it and put it together to say F equals GMM over R squared. We now, depending on how much time I have to get it, we now can retroactively understand ways in which it actually makes sense that there's an R squared in the denominator. Like, the more we investigate these things today, or like in the 1800s, the more it retrospectively makes sense that fundamental forces, that action at a distance forces, would be inverse R squared forces. Like, it's not a crazy coincidence or it's not a crazy leap of faith, as it turns out. But at the time, what it was a major induction and major extrapolation from astronomical data, if that makes sense. Or at least certainly the gravity thing was. And then by the time the Coulomb law came along, there was already gravity as an understanding in the background. So there was like a hope and a predisposition and a predilection on the part of Coulomb and others. They certainly were very influenced by already having the gravitational notion in their minds. So they weren't working from scratch by the time they came up with the Coulomb law. I don't know if I'm really answering that question right. It is a very good question. And it kind of is like a whole course unto itself, but just let me know if I sort of answered that. But hopefully you're going to, well, you may start seeing, as I discuss fields more, why the inverse R squared thing actually is not as crazy as it looked. Oh, yeah, they came from empirical data. That is, yes. particularly astronomical. Yes, they were not. I mean, there are logical underpinnings and logical reasons for them, but most of those logical reasons we now understand in retrospect. Like they really came from empirical data in the first instance. Yes. Yeah. Good question. Okay. Wait, Okay, now this thing I'm doing now, I should be, this is really covered in the other video that I asked you to watch. So I don't want to wait. I mean, it's so important. I can't resist doing it for a moment here. I don't want to be too redundant or waste your time, but let me take the risk of taking a moment. And I ran out of space here, so you forgive me, or you may want to I'm apportioning different spaces to this just because I ran out. Not there's no reason that this bottom thing should be smaller than the top, but okay. Let me just quickly say what you're seeing in the middle of the page here. This is an example. This is a vector field diagram of a positive point source. This is one way of picturing what the electric field from a positive point source of charge would be. Like if we have this positive point, like a proton sitting somewhere in the universe, or a proton or a coulomb of charge, like a whole bunch of protons squeezed together into a tiny point. But if we have some infinitesimal volume with some magnitude of positive charge sitting somewhere in the universe, when we say that it creates a field, an electric field, the way to picture that field, at least at first, is to picture that everywhere in space, there's a little vector sitting at every point in space. Now, of course, I don't literally mean like a plastic arrow or something. Like I'm not crazy as all this sounds. But a vector is a representation, right? A vector is an arrow that represents a quantity with magnitude and direction. And a vector, in other words, is a representation, is our mental model for a certain type of bit of information, a quantity that not only is a number, but in fact points in a certain way. Now, so I'm asking you, when we put a proton somewhere in the universe, picture that then everywhere in the universe, there's in your mind, a little mental vector at every point in the universe. And the vector has a certain length and a certain direction or certain orientation according to that point source of where we put it, so all the vector, no matter, you pick any point in the universe, any point at all, and you'll find a little arrow there that points away from our point source, right? So if you're over here, the arrow would point like northwest or whatever. And if you're over here, the arrow just points north or whatever, just like in the picture. So the little arrow is showing that there's a push waiting to happen. And the arrows, as you get farther and farther away from the point source, the arrows get smaller and smaller, smaller and smaller. So the direction and the the direction and the size of each one of these arrows is representing or capturing or conveying how hard and in what direction a hypothetical test charge of 1 positive coulomb of charge, how that would be affected if it were placed at that location, right? What we're saying is that there's arrows everywhere. There's these pushes waiting to happen. Each arrow represents a certain number of newtons per coulomb, pointing in a certain direction, and they're all pointing out because we assume that nothing's happening yet, right? It's just a field. It's information. It's a push waiting to happen. There's no push. There's nothing until we come along with some second charge. Now imagine that second charge. Imagine what that second charge could be. This is what we call a test charge. If we just imagine 1 coulomb of positive charge being placed somewhere in this field, if it were positive, it would be pushed away from the original positive. Hence, all the arrows are pointing out, right? They're all pushes because a positive would push on another positive. And the farther away we place this 1 coulomb of test charge, like the weakerly it would be pushed, and it would be pushed in the direction of away, but it'd be pushed weaker because these are inverse R squared forces that we're talking about. Right. So what a field is, you can think of a field as a big forest of vectors that are in a certain pattern and in a certain, they're in a certain pattern of orientation and size. And each one of those arrows, the tail of each one of those arrows represents what would happen if 1 coulomb of positive test charge were placed at the tail of one of those arrows. And please somehow in your notes indicate, first of all, notice I'm just drawing representative arrows. I'm just drawing sort of like a nice symmetric collection of the arrows that I can draw. The idea is that there's arrows everywhere, right? And again, when I say there's arrows, I'm not asking you to believe that there's styrofoam, arrows, but I'm asking you to believe that there's information everywhere in the universe that can be thought of in our mind. This is the simplest way we can think about it in our minds. Otherwise, we got to think of like numbers and like rubber bands. I don't know, like what, but so this is a vector field representation of the larger field of pushes that are waiting to happen. Let me just try to write. So if there's nothing else, if nothing else I'm really trying to get across right now, it's 2 things. 1, each arrow shows what would happen if a positive 1 coulomb of test charge were placed at that location. You see, we call the creator of the field the source charge, but we call the recipient of the field the test charge because it's a test, it's a hypothetical, it's an if-then kind of thing. If there were already a charge there, then we would just call this a force and move on with our lives. We're saying that this phenomenon occurs even before this necessarily must occur or must be there, even before the second charge comes along to experience it. This is something that is plunked down in all of empty space by the very first object that we put into space. And we are arguing that this happens as a result of or from every single little object we put in space. Like every little proton in space creates this thing. Also, every little bit of mass, every kilogram creates a gravitational equivalent of this. Okay, but we're just saying that when things exist in the world, they send out the information of them, like everywhere in this symmetric way. Also notice it's symmetric because space is symmetric. Space doesn't know the difference between up, down, left, or right, or whatever. So if you just put a dot in space, it's sending out arrows it's sending out arrows in all directions equally. And the arrows are all symmetrically pointing away from that dot, saying, I'm pushing, pushing, and pushing. If you get in anywhere, if you are test charged, that you find yourself over there, you're going to be pushed like that. If you find yourself over there, you're going to be pushed like that. And if you're 2 coulombs, if it happens to be 2 coulombs of charge, well, what I'm telling you is how hard I would push per every 1 coulomb of charge. So if you're a 2 coulomb of charge and you find yourself there, you're going to be pushed twice as hard, right? That's where we say like E is F per Q. Therefore, F is Q times E. If you want to know what force will actually be exerted on some charge that actually finds its, if you want to know the charge on, if you want to know the force on a charge somewhere in space, you ask what the magnitude and the direction of the field is that it's in, and then you multiply by how big it is, because the field is telling you how much of a force there is per every 1 unit coulomb of charge. So that's the first thing I'm saying here, is that this is, the force that's waiting to happen per each unit of potentially or of hypothetically receiving test charge. Notice again, I'm saying that the field is the forest of vectors that gets placed everywhere and anywhere in space, like automatically. And they're not moving through space. They're just there. They're just telling you how. I mean, they could be, but I'm just saying, as long as you're sitting still when the field is sitting still like this. Also, please note, and this is in the other videos too, and really the other videos will capture this from a different angle, and it is worth it seeing this more than once. I mean, it's an abstract notion. But also note that what each one of these arrows is telling you is what would happen to positive 1 coulomb of test charge. So hence, if we go down to the squeezed picture at the bottom here, if we were to ask what would happen if we had a negative source charge, like what kind of field is produced by an electron that we put in space? Well, an electron will also produce a forest of arrows, of vectors, all pointing and all getting smaller and smaller as you get farther away. But the arrows that we draw associated with an electron, we draw facing in. We say electrons pull, because we're still consistently maintaining this convention that what a field is, or what a field picture represents, is what would happen to 1 positive coulomb of test charge. Like, no matter what, I mean, this is a little confusing until you get used to it. When we look at fields, we're looking at what sources do to the universe. When we look at fields, we're looking at the information plopped into the universe, into space, by source object. The way we understand, so we're looking at forces waiting to happen, just as a convention, just to be consistent, just to keep ourselves all consistent. We're literally asking the question, what would happen to a positive test charge? Put another way, if you want to put this in your notes, and like I'm telling you, I mean, this messed me up for a semester until I realized this. Like, I didn't get the test charge. We're always assuming that the test charge is positive. Again, remember, it's a test charge. It's not actually there. If it were there, then there would be a force we were talking about. But the test charge, the hypothetical recipient of these newtons per coulomb, we're always assuming by convention to be positive. Therefore, the source, since it can be either one, it can be positive or negative. The source, if the source is negative, then the arrows are pointing in, because what would happen to a positive test, to a positive recipient, would be that it'd be pulled. Like, let me see. Wait, yeah, wait. So Sam's question. Wait a minute. This is a very important question. It may be. I have to be. So Sam's question is: would the field line diagram, would the field vector? So these are vector field diagrams. I'm going to give you a different type in a second. But so these are vector field diagrams, and she's saying, Sam's saying, would the field vector diagram for a negative test charge look like a diagram made for the gravitational field? That's a great question. Let me be careful about that. If what that question means is would the field diagram for a negative source charge look like the diagram made for a gravitational field, then the answer is definitely yes. And it's a great question. And in other words, the diagram that I squashed at the bottom of this page, where all the arrows are coming in, what I totally agree with, what I think Sam is saying, is that that diagram at the bottom of the page, even though it's squashed, but that diagram with all the arrows coming in is either the electrostatic field diagram for a negative point charge like an electron, or as Sam is saying, yes, it is equivalently the gravitational field for a source mass. In other words, what I'm totally agreeing with, I think Sam is saying, and I have to be careful about this in a minute. I mean, I'll show you why I'm being careful in a minute, but what I believe Sam is saying is totally dead on the money, spot on the metaphor, is that the field line, the vector field diagrams for negative source charges look exactly like the vector field diagrams for gravitational masses. All gravitational field and vector field diagrams, the arrows always point in, yes. And when it comes to electricity, they point in only for negative charges, whereas they point out for positive charges. Negative sources in electricity act like masses do in gravity. I believe that is what the connection that Sam's making, and it's totally right. The only reason I'm stuttering a lot, well, first, oh yes, okay, good. Now let me just say to everybody, just because it's written in the chat, and just because like people might be, and because we all take Sam seriously, so let's. I just want to make sure that if you look at it, and this is not a correction, this is just like for the sake of like us all being on the same page. She wrote with a field line diagram for a negative test charge. I think she meant negative source charge. Just to say to everybody, and yes, I mean, yeah. Oh yeah, okay, cool. And I'm not, okay, cool. So just to, okay, all right, so I'll just move on. All right, we're all good. So yes, great. Now I'm gonna do one more thing. Look at the time. You never give me your money. Oh yeah, okay, one thing. Okay. So I'm gonna do one more thing, again, at the risk. This is a little bit, and again, that video, we're going to move on. Like, I'm going to do one more thing like about these pictures. And then I want to relate it to what you're doing in the lab, which is not part of those videos or that long video that I asked you all to watch. I know it's so defensive at this, but it's just like asynchronous learning. It's a new territory for all of us. So I just want to make clear that even though there's a little bit of an overlap between what I just did and a certain section of that video, like that video is 2.5 hours long. There's a lot more in it that I didn't just do. And what I'm moving toward in a minute is totally not in that video. So the whole thing is not redundant. It is worth your time, and you get points for watching. So let me go one step further. These diagrams, okay, these are vector field diagrams. They are the first sort of way I want you to picture fields. When I picture a field, or the first way I often picture a field, is I picture a forest of vectors through the universe. Now, like the field from a proton is a bunch of arrows placed everywhere in the universe. Now, again, that's a model, it's a representation, right? It's just in my mind, but so is all of science. The important thing, the important takeaway of that picture is to understand that when we say field, what we mean is it's information that is sitting at every point in space, and it's different at different points in space. Like what a field really is like a little bundle of information at every little point in space, a bundle of information that is a description of what thing made the field, like how big it is and where it is. And of course I'm saying like I'm also saying these are vectors so that you understand like this is just the field from one point, from one little proton. Right. Then, of course, there's another proton next to it that's doing the same thing. They're both sources of fields. So what in reality happens is that every point in space has a bundle of information that is the vector sum of all of the vectors that landed at that space from all of the sources making it. I mean, these are vectors in the sense that they behave like vectors. They add like vectors. Their components add, blah, 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 blah. So if you want to know what's really happening at a point in space, like what would happen if you placed a test proton there, what would happen is what the field at that point is would be the net, the sum of all the vector contributions coming from all of the things in the universe, like like a field is really a vector sum. And vectors are quantities with magnitude and direction like this. Now this is what we picture, but this becomes a lot to picture. This means that every time I'm picturing a point source, I'm picturing all of these arrows, like that's a lot of arrows to draw every single time. And especially if those are even just a representative handful of arrows, it sure is a lot to draw. So what we do is we simplify our life and we come up with a new model. We go one step further from this, and we invent something that instead of called a vector field diagram, we now use something called a field line diagram. Again, this is in the video, I think, and maybe explained in slower detail. But okay. This is a seemingly small adjustment that I just made to the other picture, but it ends up making a huge amount of difference. All I did was take all my little arrows and I connected them up. I like in the vector field picture, that it was just a representative bunch of arrows that I drew. Of course, the idea was that at every point in space you pick, there is an arrow sitting there. I drew just enough arrows that we could see the pattern and sort of infer what size and what direction of arrow we would find if we picked any random point in space. So I'm doing the same thing here, only I connected up the arrows. Here, in the same way that in the other picture, it's understood that the picture just like goes on forever, that those arrows get smaller and smaller forever and keep like extending out radially from the center. Same thing here, it's understood that this picture goes on forever and the arrows extend out forever, but I no longer make smaller and smaller arrows. There isn't a separate vector at every point in space. In fact, at no point in space is there the tail of a vector. The tails are only at the source. This is a different way of drawing the other picture. It's a different way of representing or conveying the same type of information as the other picture. But it ultimately is a much more powerful, certainly more convenient and more powerful way of drawing it. And ultimately, this is the way we end up picturing and discussing fields in our minds. Like this idea of field lines is how we end up really modeling fields in our minds and in our computations. The field line diagram is much like a free body diagram for Newton's laws in that, and it's much like vectors themselves in that it looks like a rough sketch because I'm a rough sketcher. It looks just like, oh, okay, this is basically the idea. And when I draw, that is what it is, just basically the idea. But what it actually is when drawn rigorously and to scale, when rendered by computers, for example, this becomes itself a computation, an accurate tool for computing and predicting the magnitude, the direction, and the consequences of fields at every point in space. Let me show you what I mean. So let me show you what I mean for a moment. I'm going to switch screens if I can. Bear with me for a second. I mean, you can do this at home. All I'm going to do right now, hopefully I didn't just lose you. All I'm going to do right now is type Google in Google. I'm just in Google Images. I'm just going to type in electrostatic field line diagrams or field line diagrams. Like it's not, I'm not doing anything obscure or advanced. Yeah, here we go. Okay. Right. Okay. So I'm just going to switch screens here for a moment. Oh, I don't know how that happened. Sorry. Okay. So that's just me random. You see, all I did is type in field line diagram into Google Images, right? We could get much more specific if we wanted, but I just want you to look with me for a minute at all these different types of field line diagrams. Like what we started with, well, here, we're starting with, just trying to, oh, I'm sorry. Well, now comes the moment where we all learn that I don't even know how to use Google. Okay, well, look, notice like over here where the cursor is, that's a field line diagram from a positive point charge, as I just drew. Then here's the field, then next to it is the field line diagram of a negative point charge. Now it looks like a vector field diagram, right? It looks like just a bunch of arrows, only the arrows are now connected up. But then notice what happens when we start using this technique for drawing and picturing the field that results from, say, I'm going over here now, if this were, why can I not even like, well, okay. If I go, yeah, if I go to here, what we have here where the cursor is the field line diagram of a dipole of a positive charge next to a negative charge. Notice this is no longer, this is very different from a set of arrows. I mean, it is arrows, but the arrows are doing something very different now from what vectors normally do. Notice that these vectors can curve, not these vectors, these arrows, for one thing, they can curve, which vectors never do. They never seem to end, like they don't seem to actually have tips or tails. They just seem to have orientations, and that is the case. And notice that in many areas of the diagram, they're very close to each other, and in other areas, they're very far from each other. There seems to be always like a pattern of some kind of smooth symmetry or organization to how these arrows are drawn, but they certainly are not just a bunch of rigid, finite arrows. These are called field lines. This is how we picture the universe to be now. Like this would be the surrounding space from just a dipole, from a proton and an electron, or like a positive charge and an equal magnitude negative charge. If we went down to to say here, I don't know why I can't like even double click in the old fashioned way, but if I went down, I'm just looking to see, is that what I meant to do? Sorry. No, if I went down to, yeah, like here, where it says other charge configuration, like here, again, we have a positive charge near a negative charge. Yeah, sorry, we have a positive charge near a negative charge. But here something is not symmetric in quite the same way as before, or is it actually? Let me get a more vivid example. Here, I'm sorry, a more vivid example. Okay, yeah. Like there is positive next to negative. Then in the middle here where the cursor is positive next to positive. Then here is positive next to negative, but not of equal magnitudes. Now, I don't know if you can tell on what intuition I'm basing these descriptions, or yeah, and same thing up here, like, right, like here where the cursor is, if you could tell, that's positive next to positive, but of two different magnitudes. Here is positive next to negative, but of two different magnitudes. Now, how can I tell, or what am I talking about? What's going on here? Well, these, and this is how we picture the universe. Like, remember I said a minute ago, when you're anywhere in the universe and experiencing the field, you experience all the vector, you experience the vector sum of all of the vector contributions from all the stuff generating fields anywhere near you. So what you end up experiencing can be very, very the result of a many complicated set of factors. The way the universe looks, the way space looks, ultimately can be very complicated. What we were drawing a minute ago on the paper was the field line picture just due to one point. The minute you start having more than one point, you have more complicated net effects. But we capture these net effects with this representation or this model called field lines. And it's ultimately the way we actually end up talking about these effects. We end up talking about field lines in the universe, and we'll end up making arguments and calculations. Like we'll say, well, the field lines from the proton over here are doing this. So then that thing, when the field lines, blah, 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 we talk about them like they're real. Just the same way that once you get used to vectors, you talk about vectors like they're real. Now, nobody literally thinks that there's literally arrows sitting in space or literally lines sitting in space. But we don't literally know what there is in space, right? We're not trying to get you to believe in something that you don't want to believe in. What we're actually being is humble scientists and saying something is going on in space that's beyond our comprehension. Somehow, information sits in raw space and gets transmitted from one object in raw space to another. And it's like and it's happening all the time. And it's happening in evidently a way that we are managing to make predictions about and calculations about that are fairly advanced. But the way we make our predictions and our calculations, we come up with models in our mind that work for us. We're not literally arguing that there are lines in space, but we're saying if we picture lines according to a set of certain rules, just like if we picture numbers and mathematical systems according to a certain set of rules, that seems to give us power to somewhat predict and manage nature. So there are rules for drawing and reading these lines that allow us to then represent what the fields are doing in space. Now, I intended to relate this all back to currents and potentials for your lab. I know we only have 6 minutes left, so I'm not sure I'm totally going to be able to do that. I'm going to try, but as long as I'm on this whole tear right now, I'm going to give you one more page of notes to tell you how it is to read these diagrams and make these diagrams, so that from now on, when we talk about fields, we can talk about field lines and we'll know what we're talking about. So I'm going to switch the screen back. I'm just going to go on the next page for that. But and I know we have 3 minutes. I just want to give you a couple of these rules and we'll be done for today. But just to understand what field lines are doing, field lines, what all they are is all the vectors connected up, but that ends up meaning they have a whole different character. So first of all, notice field lines, they come from positive or they come in from infinity. And then they land on negatives or they go off to infinity. Now you might say, as I did when I first heard this, like, well, duh, like what other option would there be? I mean, what do you mean? Like they come from positive or from infinity, like as opposed to what, yo? As opposed to starting or stopping in empty space. What we're saying with this rule number one is you never see the tail of any of these arrows just sitting in empty space, and you never see the tip of any of these arrows sitting in empty space. Field lines don't start or stop in empty space. They go from positive to negatives, or they go from positive off everywhere, or from everywhere into negatives. You see what I'm saying? They don't start or stop in empty space. That's the first. There's just a bunch of arrows that are connected up. That's the first thing. The second thing, and again, I'm watching the clock. I know we have 2 minutes. Just bear with me for a second. Rule number two is okay, almost self-evident, but not quite. And I'm watching the clock. We have 2 minutes. So if you draw a proton, you come up with a scaling factor in your mind, whether you're just sketching or whether you're computer rendering, you come up with some scaling factor. Like I'm going to draw out 5 lines for every 1 coulomb of charge that a thing could be. So if you have a 5 coulomb source charge, you would draw 25 lines coming out of it and all coming out symmetrically because space is symmetric. Then they would either go off to infinity or they would land on any negative charge that there might be, right? But the number of lines that connect to a thing must be proportional to the thing. So you notice, like I was noticing in that diagram, the more lines there are in an area, the more charge has generated them, which leads me to this, and we're just about done, I promise. With vectors, the length of a vector indicates its magnitude, right? Well, there's no length here. All these lines are going off to infinity or going on. There's no length to these lines. So how do we infer magnitude of field? The magnitude of field is directly proportional to the density of lines. And I see that it's 1:30, so we're just going to write that and that's it. The more lines you see, the stronger the field is. Not the longer lines. The more lines you see, the stronger the field is. And this is the very last thing we're going to say. And have a nice weekend. Lines can bend, but never cross. I'll just leave it at that. And they never cross because the line is already itself a representation of the net effect of all of the vectors coming in and adding. So the line is already what would happen if a bunch of vectors crossed and added up. So the lines themselves never cross. I'm going to leave it at that because it's 1:30. You've been very patient. I know that didn't actually end up helping with the lab. Well, hopefully it helps you. I don't know what to say, but we needed it. And have a great weekend. Have a great weekend.